And I've been thinking about galaxy formation for the last 10 to 15 years. I'm fascinated with galaxies as most people are. Because I like to think of galaxies as speech. Like if you meet me and you pay attention to my accent or the way I move my hands or the music I listen to or the people I like, you can infer something about my history, my ancestry, my family. Galaxies are like this. When you look at galaxies and pay attention to the properties, you can infer something about their history, the impact of these galaxies. So, but before I begin, I want to acknowledge that I conduct all of my work in the indigenous family of Donga Gravity. I am a person of indigenous ancestry, who have actually was therefore really important for me to make this acknowledgement. Also, I'd like to acknowledge the people who clean our offices, who bring our food to the table, people who didn't have access to the education that we do, but they are involved with the universities that we are, except that they didn't have the privilege. So everything we do, we need to acknowledge. And also, I'd like to thank my collaborators. We wrote this paper, it was published in Astronomy 3 months ago. It is mostly the prior collaboration, which ended and was concerned. And also the Downing College, Cambridge, they might visit here. They're awesome. And just a little bit of an outline of what I'll talk about today. We'll just start with a background, looking a little bit of what these galaxies are. There's been a bunch of debates about these galaxies. And many of the people who have participated in the debate are actually engaged. I think it's going to make this competition quite exciting. Then I'll talk about firefox, which is a more difficult simulation that I use. And then I'll talk about other simulations. It turns out that other cosmological simulations have been able to reproduce this kind of galaxies. I'll talk a little bit about why I think that's the case. And then I'll talk about the physical mechanisms that could explain this intelligence. So, as I'm splitting this talk in chunks, every time I finish one of the chunks, I'll give you a mini review, and that's a good opportunity to ask questions. Or you can just save your questions until the end. But please ask questions. So a little bit of background. So this is Andromeda, and it's very dynamical mass. It's all mass what people use is rotation. So you measure the redshift and redshift, and then you can get the rotational velocity, the circular velocity as a function of distance from that rotation. And it's using my mechanics, you can infer the dynamic mass, total mass, which could be in gas, stars, and mostly dark. So this is how we evaluate rotations for the system, like spiral galaxies. This is what they're doing for the way. But when we have elliptical galaxies, so two orbital spheroids, this partially supports this to not this system. So what people use is estimators like this one. But basically the idea is if you measure the size of the galaxy, and you measure the length of the velocity dispersion. How do you do this? You measure the velocities of your stars on the line of sight direction. You draw a histogram in a galaxy with this sigma. So if you know the sigma and you know the size, you can infer the dynamics. And people find that most galaxies are dominated by outcome. But I want you to remember this. And the other thing I want you to remember is when we go into the low mass regime, we're looking at this so-called dwarf galaxies. All the stellar mass goes down, the dynamical mass goes down, but actually the fractional mass in dark matter actually goes down. The tinier the galaxy, the more dark matter dominated it's supposed to be. I want you to remember that. And we can explain this in two ways. One way is with abundance matching. So here I'm showing you what we call the stellar mass. It is basically telling you the average number of galaxies in the given stellar mapping for the bottom. So for example, if we look at galaxies of 2 times 10 to the 11, we're likely to find one in a volume of 10 megaparsecs cubed. So if you take a volume of the universe that has 10 megaparsecs by 10 megaparsecs by 10 megaparsecs, that is cube, and you move it around, on average, we will only find one galaxy. And you can do this the same way here. So before I was showing you the stellar mass distribution for galaxies, if one you observe, when you're simulation, you can also count the number of halos that are going to follow. So the black line would be dark matter halos. The dashed line would be a correction if you account for the fact that there is only fraction of variance in the universe. And you can say, for example, if I'm looking at halos of 4 times 10 to the 12 solar masses, there should only be one in a volume of 10 to the 3 megaparsecs. On average. So that's what we call this abundance. So what we can do is we can put it together. And we expect that in this kind of volume, we expect one such galaxy and one such halo and you match them together. You can make a mapping between the most massive galaxies in the real universe with the most massive halo. And you can use that data abundance, like this one, you will match it with. And then you go down and you can match it too, and so forth. And for every galaxy stellar mass, you can assign a dark matter halo mass. And notice that the gradation changes. Like if you go to the massive level or the low mass end, the discrepancy between stellar mass and halo mass is bigger. But when you're around super around the Milky Way, actually that discrepancy is small. There seems to be some sweet spot in our galaxy, in this regime, where the discrepancy between halo mass and stellar mass is minimized. But if you go into supermassive galaxies or super tiny galaxies, they become more and more dark matter. Another way to think about this is in terms of physics itself. If every barrier in the universe converted into stars and those stars were locked in galaxies, the dashed line would match the direction. But in reality, that doesn't happen. There is a lot of gas out there that will never get in stars because you have. If you went to the massive end, the reason that gas won't go into stars is because you probably have taken the supermassive black holes, which are keeping this gas ineligible for salvage. And when you go to the low mass energy, it's usually stellar processes like supernova feedback or winds or other things that keep the gas from converting into stars. So a way to think about this is around the Milky Way scale, that's where the process of gas formation, process of converting gas into stars becomes a bit. What does this have to do with galaxies without dark matter? Well, because I want you to keep in mind that we can map the stellar mass of the galaxy with the dark matter mass of the halo, and you can actually plot one against it. You see that the means around the Milky Way, but once you go down, then the system becomes more and more dark matter. For example, if I look at 10 to the 9 solar mass galaxy, the ratio of the total mass to the stellar mass is around 1 to 20. But once you start going into the low mass region, the number increases to 2,000, and when you like the ultra faint goes up to 20,000. So by this matching process of using the stellar mass function in the real universe and the halo mass function in the simulated universe, we see that when we go to the low mass regions, the galaxies become more and more dark. Now, the other piece of evidence is actually measuring this indirectly, and this is what Eric covered a bit ago, where you measure the stellar mass within some effective radius of the galaxy, and you measure the dynamical mass using the methods mentioned. And he showed that when you go into the low mass machine, you become more like in the y-axis, I'm showing the light mass ratio, the mass to light ratio, and that mass to light ratio goes up when you go to the tank. I want you to remember that. But just to summarize this intro, we use rotation curves to infer the dynamical mass in rotation support systems like spiral galaxies. We can use the line side velocity dispersion and the skeptic radius to infer the dynamical mass in dispersion, like in the galaxies and Jorge experiment. And when you go into the low mass regime, galaxies tend to become more and more dark matter. Are there any questions about this? And if you have them and you're shy, you can always ask. Going once, 25. All right, so let's talk about dark matter. So this is zooming into the group in this country. Has gotten the Galaxy group, and we're zooming into a dwarf satellite. What I believe is satellite. It is NBC PF2, which looks really weird. It's very open issues, and it seems to have this weird population of low galaxies. This galaxy has gotten attention. And this is Shani Lily and her supervisor, Peter Van Lowe, the Explorer Galaxy. And they use Dragonfly to discover it, and then they follow it up with Keck and Hubble. And what they did is they look at the globular clusters to measure the line of sight velocity. So that way you can measure the dynamical mass. So this is the line of sight velocities. If you look at the white histogram that refers to galaxies in that group, But if you look at the gray histogram, those are the orbital clusters inside the galaxy. So that's where they are. If we switch to, so you can measure the stellar mass, and it's around 28. And because I was telling you about before, when we went to the low mass, we expected in bigger cables. The expected line of sight velocity expression for this system should be around 32 kilometers per second. And what they observe is it's actually lower, it's 8.4 kilometers per second. Basically, the dynamic of mass is tiny. So if you take this estimator that I told you about, measure the size, we measure the mass of the dispersion, the so-called dynamical mass, and you get that the dynamical mass is more or less consistent with the mass, or that there is no government, which kind of like threw us off. Maybe those were kind of a concern. Maybe there's something wrong with the model. Maybe there is something wrong with the observations themselves. And let me talk a little bit about that. So, and actually, the year later, they found another one in the same group. It's before. I don't like saying the two numbers so much, so I'm not going to get it for now. And this is what the group looks like. So here's the, this is the, I'm going to use my mouse for the benefit of people. So that's the X2 and the X4. And this massive galaxy in December is this dominant galaxy below you. But also I need to pay attention to these other galaxies. The one from Jorge, 1042 and 30. So I might mention them. And talking about some of the debates that people have, having one of them is distance. So Van Gogh and that group, they say, oh, these galaxies are 23 megaparsecs away from us. And then people repeat it, like Nacho here and A and others, but say, you know what, actually, this is probably closer to us. And if this galaxy is closer, probably we're underestimating the stellar mass. Maybe this galaxy's stellar mass is actually higher, and therefore this is star higher. And there's things of John reveals. Be happy to talk to the experts about that. Another debate has been the tidal distortion. These things are actually interacting with different galaxies, right? So there's been, for example, they explained that EF2 doesn't have tidal distortion, and or that, and then there was a zero here, and also I like this one where it's EF4 is actually has tidal distortion, but it's not associated with the most massive galaxy of the group, or rather the one I told you about, which is actually the massive. This is Mireille, I mentioned this. I think it's a galaxy that is around the same mass as the large timeline top. Is that right?
I don't remember. What's that out of the number? My source is 1035.
More like 1033. Yeah, 1030. So it's not like us. It's not like the central galaxy. And but another thing to pay attention in this debate is not just the presence of tidal distortion. And if we're looking for tidal distortion, there is something that I think we want to assume there is a massive galaxy causing this galaxy. But another thing to pay attention to is something that I think is things like we have to have a little bit of rotation, right? So before I was telling you, for rotations for the system, you use rotation curves. What is person for the system to be possible to show you. But what if you have something that has both? So if you have a little bit of rotation, then you're assuming that it's only dispersion dominated, it's actually you're underestimating the time. So it could have more time. So, and the last thing I want to mention is, in addition to this kind of galaxies, people have been finding galaxies that are also dynamic efficient, but not because they are pouring stuff, but because they're reaching gas. So Chibo in China and Pavel, Mancera and they found galaxies that have a lot of gas, and they claim that also dynamic efficient. I will not talk about this kinds of galaxies in this talk. I will only focus on this gas component. And okay, so now let's talk about what we can do with situations. If these galaxies are actually what they are claiming, these galaxies are low-mass galaxies with little or no mass, can we reproduce them in close knowledge? So that's the question I ask. So, and to do that, I just fire this. Thank you for that. No, is this better? Well, can you send I don't know.
Yes.
Well, I'm very nice. I never teach it on a microphone, but I never thought it's working. Apologies, like, let's think that I hadn't talked about Firefox, which is the big one. But anyway, just going back to what I said before, the time person. So the question I ask myself is, if these galaxies are active, if these galaxies are actually dark matter efficient, low mass galaxies, can we reproduce them in cosmological conditions? If they appear in our created universe naturally. To do that, I use Firefox. So fire sends the feedback interface environments. And with that, this is the first time we run a full cosmological simulation and high resolution. Now the fire collaboration, what we usually do is we run cosmological boxes of low resolution. We focus on a sample of galaxies, and then we zoom into those galaxies. We follow the Lagrangians in space back in time. We resimulate everything at super high resolution, and then we get a bunch of galaxies in isolation evolving at high resolution. So that's what the Spire actually does. This is the first time we actually run the whole box at really high resolution. And in my opinion, this is really revolutionary when it comes to cosmological simulations. For example, if you go back 10 years ago, you can think of the Millennium simulation with suns. Then we jump into the higher simulations like Greenhouse and industrial simulation. I think this is a big enough. This is even the Microsoft. So this is a really cool simulation. And let me tell you a little bit about it. So when you run a cosmological simulation, there are two things you want to optimize. You want to optimize the resolution, because if you have really high resolution, you can really resolve galaxies with a lot of. You can really get those. Another thing you want to maximize is the volume, because if you have a really big volume, then you will get a representative chunk of it. So you want to maximize both, but both are expensive. Because if you increase resolution, you need more particles, making your volume grow with more particles. So what we call that combination discovery strength. So this is where Firefox is. Today I will talk about Firefox yet. We also have Firefox high resolution that's a redshift right now. It's still running. I won't talk about it. So I'm using the low version. And if we compare with other simulations, these are some simulations like the one I told you about. Firefox is comparable to the resolution, but it has a bigger volume. Or we can talk about some of the large volume simulations, like Illustrious TNG or Eagle. And they do have bigger volumes, but in terms of discovery space, are comparable. Now, this is one way to quantify cosmological simulations. Another way is to actually compare Apple properties, compare the spatial scale. So what we do is this we call dynamical range. So you could be actually looking at spatial resolution versus the volume. And this is where Firefox is. This is where the zooms are. And this is where the large volume simulations are. So in terms of dynamical range, we beat every simulation out there, zoom or cosmological. Does that make sense? And for the experts, something to mention is the symbols that are solid. Those are symbols, those are simulations that resolve the multi-phase structure there. So let me just give you a glimpse of what this looks like. You can take a chunk of the cosmic web and zoom in some more, and some more. And we have the physics and the resolution to actually handle the properties of giant molecular clouds with some reasonable and this is one of our Firefox galaxies. This is a visualization. And it's pretty neat. And to think that this is actually embedded in a cosmological box, you think that so much detail and so much physics, and you get a lot of numbers. This is a mock set of images in a video of one massive galaxy. This is STAR. This is we use gradient transfer to create a mock optical image. Right. So what do we get? So now I will focus now on low mass galaxies and look for dark matter diffusion galaxies. So what I'm showing you here is on the y-axis, I'm showing you the mass in dark matter. On the x-axis, I'm showing you the stellar. Now, Van Dolfen and Daniele, they focus on the half-life radius, effective radius.
So that's what we're gonna be doing here. All I'm saying is here is quantities within the half mass. And this is color coded by the fraction of mass in dark matter. So if you're really pink, it means you're dark matter dominated. If you're really cyan, it means you're dark matter deficient. And let me add some lines to guide the eye. I'm only showing you central galaxies, and that bar is telling you the average. And you see that the slope is below unity, which actually explains why when you go into the low mass regime, you become more dark matter dominated. The solid line divides the dark matter dominated and dark matter deficient regime. And this is where you would find DF2 and DF4. Now, the reason you don't see any simulated galaxies down there is because I'm only focusing on central galaxies, like the note today. So galaxies have satellites. Satellites have subhalos. Sometimes satellites have their own satellites, and those subhalos have subhalos. So once I include all that substructure, this is what you get. You get that things deviate from the main relation. They go down because they lose dark matter, and they go to the left because they lose stars. So they usually go like this. But a few of them, 7 of them, are actually below the line. 7 of them have more mass in stars than in dark matter. Especially the one at the bottom pink, you only have 1% dark matter within the detected zone. So I gave them really cute names. These are the names: wolf, wild potato, pain blue, long hair, bird, and deer. So I found 7 galaxies, and I asked myself, well, maybe I can select some names. I asked my collaborators, they said the Disney character. I was like, I don't like, if I were a small person and I read this paper, I would probably feel kind of shitty. So I was like, I'm not gonna use that. I thought about using the 7 sisters in Greek mythology, but I'm not a woman, and I felt I wasn't also my place. I'm someone with indigenous ancestry. I have friends with Cherokee, and we asked the elders if we could use the name for the clan, and they said yes. And each clan has a personality, and each galaxy has a personality. So let me tell you about them. Let me introduce them. So this is Wolf. This is a mock Hubble Space Telescope image. And Wolf is a satellite. And this is the dark matter map. So this galaxy doesn't have a subscale of the spirit, or at least it's not visible. This is the spot potato. I will please pay attention. And this is its subhalo. Here it's paint. Paint is a little bit, this is the 40 one. And this is its, there's no subscale. So I have a question for the audience because I like interacting with people to see if they're paying attention. My question to you is, what do these 3 galaxies have in common? I'm talking about the tiny galaxies in the circle. So they're interacting with a massive galaxy that is right next to it. Anything else? So this is students. They're small. He's speaking on your behalf. So they have tidal features. Are they blue? No, right? They're probably gas pool. They're probably not making stars. They probably haven't made stars in a long time. So that's what they have in common. And they have very little dark matter. Now let's talk about the other 4. This is long hair. Long hair is extremely far away from the center of the halo. This thing came in, it hit the central galaxy. Its pericentric passage was 6 kiloparsecs. Launched to the galaxy. It went through the other side of the halo. It left the halo. It became a center. It always passed. And now it's on its way back. So this is an extremely radial orbit. It's like, I'm just gonna punch through it and go through the other side and come back. And this is its associated dark matter mass map. And the last 3, they're actually in this. Oh, I wanted to talk a little bit more about long hair. So long hair doesn't show tidal features, at least surface brightness. But if we go deeper, this is something we wanted to do. If you go down to like 30.5 Mach per second for 3D computing. This is for magnet. And the last 3, deer, blue, and bird. Blue and bird, they came together first time. They were dancing with each other, and they started into a group. And deer is the fluffy one. Deer is also a backsplash galaxy. It also went through and left the halo and it's on its way back. And this is the dark matter. this is the image I made when I decided to write the paper, and because my focus has been on galaxy mergers to massive galaxies, but this was like, this is kind of cool. So just to so this is what these galaxies are, and just to summarize, closer to me. So people, there are claims of 2 dark matter deficient galaxies in the real universe, DS2 and DS4. We found 7 in Firebox. They tend to be satellites. They tend to have tidal features and be red. 3 of them are very close to massive hosts. 1 is very far away, what we call a backslash galaxy. 3 are in the same group. And when you compare to the internal properties of DS2 and DS4, Wolf is the one that resembles them the most. Any questions? So they were born just like regular galaxies, lots of gas and dark matter. And I will talk about how they lose them next. Any other questions? Let's go with Chris first. So the question is, how does the environment that group, the one question 3 is similar to the one question DS2 and DS4? So it's really hard to measure group masses in observations, but you can do it in the simulations, and our halo mass of the host is compatible with the MDC sensitivity. And not sure you have a question. Mhm. Mhm. Uh-huh. So the question about the brightness of the tidal features, does it last forever? We saw that long hair is really far away and you have to go really deep. So, but I haven't done the exercise of tracking it across snapshots. That's something I want to do next. I think so. To explain that specific galaxy, yes. And the thing is, like, even the observation results are debatable. So the question is not so much, the goal here is not to reproduce these galaxies exactly because the observation results are debatable, but rather that in this cosmological simulation, you can create galaxies that are dark matter. Oh, do you mean, so I mean, if we go back to the here. So that's what we, yeah, so I think you have to go below, like, below 30. All right. So let me just go back to this slide. All right. So you're asking about mass estimates for whom, the observations or the simulations? So in the simulations, we know the mass. It's just out of the particle. I see. So the simulated galaxies, our sample of 7 are between 10 to the 7 and 10 to the 8 solar masses in a stellar. When it comes to the dynamical mass, that's something we can measure directly with the simulation using the particle. One could also do the exercise of measuring, estimating the dynamical mass the way observers do. We try that, and the discrepancy is not that big. But of course, we use the simplest Wolf estimate. We don't go use any sophisticated machinery for that. But the thing is, in simulations, we do know the real math. Are you saying like because there is diversity in the masses of the galaxies, could that explain? That's a really good question that I will try to answer in the next paper, definitely. No, for real. It's like we're looking at things like the current mass or the progenitor mass or the kind of orbits you have. All those things could play a role in what kind of, if you're a mildly dark matter deficient or if you're an extremely dark matter deficient galaxy. So that's definitely a valid question. Any other questions? I think in our simulation, you go down to like the SMC, but it's, I guess you can even go lower if you have higher resolution. So we're a little bit resolution constrained when you start looking at subtotal halos. So once we finish running the high resolution one, we'll probably get more. I found the order of 20 subtop halos in the simulation. Any other questions? This one? You're talking about this side here? So the question is, why does like 10 to the 8 seems to be the lowest one you get? I don't know the answer to that. My speculation is the following. If you're really tiny today, you were probably really tiny when you fell in. And which means that the tinier you are, the smaller you are, the more dark matter dominated you are. Therefore, it's harder to become dark matter deficient if you start off with even a higher fraction of dark matter. That is one of the reasons I think this is the case. The other one might have to do with the property of merging versus disruption, and I'll talk about that later in the talk. But that's a really good question. Keep that in mind. Why do we have this? Yeah, so either they assimilate, they merge, or they disrupt. And I'll talk a little bit more about that later. But let's keep that in mind. All right, so let's move on to the next part. So what to deal with other cosmological simulations? So I'll talk about 3 cosmological simulations today that have comparable volume and resolution as Firebox. So this is New Horizon by Jackson. This is Eagle High Resolution by Ying. And this is Illustrious TNG 50 by Laura Sales. And let's start with Jackson. So about a year ago, Jackson published this paper where they claim they found dark matter deficient galaxies. And what they did, this is the analog of their figure 1. So here they're showing stellar mass on the y-axis and the ratio of dark matter to stellar mass in the x-axis. Now, the plot I was showing you before, we were focusing on the effective radius, the radius containing 50% of the mass, as observers do. Here, I'm showing you everything. Everything in the virial radius or everything in the subhalo radius, that's what they report. And I'm showing you just central galaxies. Then we can add a line separating the dark matter deficient from the dark matter dominated regime. And that's where DF2 and DF4 would be. And if we include satellites, this is where the satellites are. And this is where our galaxies are. So our galaxies are on this side of the plane, which means that they're dark matter deficient, not only within the effective radius, but all the way out to their subhalo radius. Now, if we look at the Jackson sample, they're right there. So they kind of like, when you read the paper, they kind of say, oh, because we're below the main relation, we're dark matter deficient. But if you notice, they're all between 1 and 10. And I think, in my opinion, I wouldn't call this a dark matter deficient galaxy because it's still dominated by baryons. Even if you look at the most extreme one, like the one to the left, right next to the F4, that has a 60% excess in stars. So I'm not quite sure about that. And if you look closer to the paper, they also find the following. So here they're showing you the minimum distance between the satellites and the central in units of the virial radius of the host. And they find that all of the dark matter deficient galaxies, they have low values, but they never go within 20% of the virial radius of the host. You have the dark matter halo, you go down to 20%, they never enter that region. So I want you to remember that. Now, talking about the Eagle is a low resolution simulation. And they did a study, but they only look at massive galaxies. So we're not really going to talk about that. DF4 and DF2 are around 10 to the 8. This is an order of magnitude from the higher. But Eagle high res actually is able to go down to 10 to the 8. And this particular point caught my attention. Unfortunately, the authors didn't talk about this much in their paper. So I sent them an email and they sent me all the data I need. So I put their data point in my plot. And this is the only one besides the Firefox Galaxies that crosses this line. It's not quite like the S24, it's a little too massive and its velocity dispersion is a little bit too high, but it's a promising option. And the last one I want to talk about is illustrative. So we were talking about creating galaxies that are of the mass of around 10 to the 8 solar masses with really low line of sight velocity dispersion. This is from Sales et al. 2020 using, if the symbols have error bars, they are from observations. If they don't, they come from illustrative. DS2 and DS4 are down there, and none of the things satellites go down in that region. Whereas if you look at Wolf along 3 orthogonal directions, you get really tiny line of sight velocity dispersion for the stellar. And we can put this together. So here I'm showing you the line of sight velocity dispersion versus the stellar versus the effective radius. Those are the quantities you need to estimate the dynamical mass. Here I'm only showing you satellites between 10 to the 8 and 10 to the 9. And I can put some lines to guide the eye using that dynamical estimator I told you about. This is where the observations are, and this is where the simulations are. Some of them are too big and fluffy, some of them are too, they have really high line of sight velocity dispersions, but what they own, especially Wolf, is quite consistent with the reported observations. So just to summarize, most cosmological simulations have struggled to create galaxies like this, or to create galaxies with low enough line of sight velocity dispersion. And we're able to find, especially Wolf, is really similar when it comes to internal properties to the X and the S4. In terms of stellar mass, in terms of line of sight velocity dispersion, we also measured the Pershing index consistent with that too. So, any questions? What are the other simulations struggling? So there are many things. So one of them is the treatment of the interstellar medium. We do Fire does a really good job at capturing the multi-phase turbulent structure of the ISM. I would say the New Horizon does a really good job too. So I was surprised that they don't. That could be one reason. Another reason could be that they are not finding them. So something I found is when you have a cosmological simulation, you have automated algorithms that find this galaxy. You just run the code and you find them. So I did this. I ran this algorithm, and it turns out that the algorithm itself didn't find any of the 7 galaxies. I had to look at every halo eye by eye, and I actually had to recover those dark matter system galaxies. So either it's a problem with the finder algorithm or the way I run it, and it could be the case that maybe those galaxies do exist in their simulations, but the algorithms didn't find them. Does that make sense? It's like if you're trying to get good graduate students and you only look at their, you give them a test and you look at that score and that's the only method you use. You're missing out. I think this is what's happening here. The algorithms are not finding some of this. These algorithms were designed for dark matter only simulation. Once you put variance, things can get complicated. Any other questions? Numerically, what was happening? Okay, so let me see if I can rephrase the question. So I will talk about interactions with a massive galaxy being the culprit for this. So you're losing, you're being tidally stripped. But it could be the case once you go to low resolution that you can have numerical stripping. This is a question we got from the record. And we went back and looked at the merger trees and we looked at the regime when it became dark matter efficient, and it's way above resolution points. I think we keep running this to lower and lower, like into the future, you can run into the numerical stripping, but for the most part, we have high enough resolution for that not to be a problem. Even Wolf, which is the tiniest one, has 3,000 stellar particles at the end. And it starts with like 50 times more plus dark matter and gas at the end. But that's a valid question. Any other question? Yeah. Oh no, that's 10 to the 0. So that's the ratio. You're talking about the top panel, right? So that's the dark matter mass divided by stellar mass, and the threshold is at 10 to the 0, which is this one. So this is below unity, above unity. So why don't I show that plot again so we can see it together. So we're talking about these ones here. So the threshold is at unity. Either you are dominated by stars or you're dominated by dark matter. That's stellar mass. And I constrained this because we found before that that's what this low mass galaxy is doing. Like I checked that below 28, there's nothing. That's the active one. Right. So let's go back to the summary slide. Any final questions before we move on to the last part? We will talk about that right next. So variants do get affected, but for some, Anna, let me see if I can answer the question right now. So the question is, why are variants affected like the dark matter? Why are you stripping the dark matter and not the variants? The answer is you are stripping both, but you're stripping the dark matter more efficiently. And the reason is because the stars come from the cold dense gas, which tends to be strongly gravitationally bound. Whereas the dark matter, you have a distribution. So you can have these dark matter particles going in very highly eccentric, poorly bound orbits. Those are more easily disrupted. All right. So how do we make these galaxies? And I already answered a little bit of this by the question, but let's talk about it. So I think this picture gives us a lot of truths. There has to be a massive galaxy next to it, and probably an interaction with that massive galaxy is the output. So the first thing I did is I'm showing you the mass of the central galaxy, stellar masses of the central galaxy versus the satellites. Again, this is color coded by fraction of mass in dark matter. I can put some lines to guide the eye. This is what NGC 1052 is, that massive galaxy in that group. And that's where DF2 and DF4 are. And this is where my 7 dark matter deficient galaxies are. So one thing to note is that all of them are between 10 to the 8 and 10 to the 9, and they leading hosts are at least 10 to the 11 solar mass. If you go down to like something like M33 or the LMC or the Milky Way, they won't have satellites that are dark matter deficient. At least that's a prediction we make. We also predict that if you take all galaxies with at least 10 to the 11 solar masses, 30% should have at least one dark matter deficient galaxy. This is a prediction we make. Hopefully observers can check or falsify our comments. Another thing to notice is that they kind of follow a dynamic. So we could also say, well, actually, what you need is the stellar mass ratio of the satellite to the central should be about 1 to 1,000. So that's one condition that we find should be obeyed. The other one is just looking at the history. So here I'm showing you the distance between the satellite and the center of the functional time from the time it became a satellite, the initial time to today. So that's this weekly line. If you look at the gray solid line, that's the radius of the dark matter halo, the host. And if you look at the dotted line, that's 5% of that. And something that happened, and we can also look at the mass. This is the total mass. That's the dark matter mass. That's the stellar mass and the gas mass. So they lose their gas early on. They are losing stuff, but at a much lower rate. They lose dark matter more efficiently than they do lose like stars. And if we compare the two back to back, you notice that when it becomes dark matter deficient when it plunges into the center of the halo. Remember, I told you the Jackson paper, they show that their satellites never go within 20% of the halo. These galaxies, once they go within 5% of the virial radius of the post halo, they become dark matter deficient. So these things are not just orbiting a massive galaxy, they're actually plunging to the baryonic component of the central massive galaxy. And so this is another condition that has to be met. You need to be in extremely radial orbits, and you need to be hitting the center of the haze. So just to summarize, on the y-axis, I'm showing you the minimum distance between the satellite and the central in units of the host dark matter halo versus the mass ratio, the stellar mass ratio of the satellite to the center. And this is where DF2 and DF4 are. And this is where our galaxy. The numbers in brackets refer to the number of pericentric passes the galaxy is. And we can be a little bit more quantitative. And going back to your question from before, there are a couple of gaps. So on the right side, you have a gap. On the left side, you have a gap. Galaxies are on this side. For example, if you're looking at mass ratios of 1 to 10 or 1 to 100, what usually happens is that dynamical friction is very effective. So the moment you hit that regime, you're basically merging. Whereas if you're on this end, if you happen to even get close to the galaxy, you are completely disrupted by tidal force. This is like when you're a satellite in a massive system, you're given two options. Either you assimilate or you're destroyed. But these galaxies actually chose neither. They confronted this Goliath multiple times and they are still there. For example, this is blue, it has 10 passages, and this is vert, it has 14 passages. It keeps orbiting that central galaxy and it survives. So just a final summary. People report 2 dark matter deficient galaxies in the real universe. We find 7 in Firebox. To become a dark matter deficient galaxy in our simulations, there are 2 requirements. You have to have a stellar mass ratio of 1 to 1,000, and you have to come within 5% of the radius of the host dark matter halo. And we predict that 30% of central with masses of at least 10 to 11 solar masses should have at least one satellite that's dark matter deficient. And some of them have multiple paths, anywhere between 2 and 4. The last thing I want to say is that I feel personally connected to these galaxies for many reasons. So satellite galaxies, they are given 2 choices, either to assimilate or to destroy. And these galaxies chose to confront the problem. And this is true for many people in astronomy. If you're the only woman in the room, if you're the only Black person in the room, if you're the only queer person or the only Muslim in the room, sometimes you might feel that you need to assimilate or be destroyed, but you can actually do something about it and stand up for yourself. And I think this is what this galaxy teaches. I'm a person of indigenous ancestry, but I have European name. I speak European languages, but I'm still here. I'm kicking ass. So thank you for your generous attention. Any questions? Chris. Yeah, I can paraphrase. So I'll do my best to paraphrase your question. So the question is, well, in this talk, I've talked about 2 radii, the subhalo radius and the effective radius. But it could be that, so the question is, how does the relative presence of dark matter versus stellar mass as a function of radius changes? I did look at the profiles and they look kind of cuspy. So, but that's at the end. And I haven't looked at the profiles as a function of time. Something I want to look at is look at their progenitors, see what their profiles look like, if they're toward or cusp, if that plays a role in whether or not you're more susceptible to become dark matter deficient. Does that make sense? And I know you've written a lot of core problems. Mhm. Yeah, so yeah, Nacho. Mhm. So long hair is the one with the fewest passages. It has only had 2 passages. So it came in, it came back across the center of the the halo. It left the halo and it's on its way back. So it's on its way to the 3rd passage. So the question is, so if it's only had a couple of passages, where is the dark matter? So is now member of the host state. Mhm. Mhm. Yeah. So if you look at so the question is, so like if you lost the dark matter, shouldn't you be able to see like dark matter streams? Does that make sense? And when I look at the maps, I cannot see them. Something one can do is you can take the progenitor atom pulse, you can pack all the dark matter particles and see where they end up. So I think that would be a better way to see what's happening, because there is so much stuff in the background that it makes it quite impossible to see those structures. And that's definitely something I want to do next. It's like ask the question, where is this dark matter going? Where is how it starts going? Does that answer your question, Akta? Yeah. Yeah, and because there is so much junk in that halo that it's really impossible to see these features. Mhm. And I think by tagging the initial particles, we could see where they are, even though you cannot visually see them because of, as you said, the high contrast. And then go. Mhm. 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 So the question is, in addition to being dark matter efficient, these observed galaxies exhibit really weird globular cluster populations. And the question is that something we can resolve with Firebox? The answer is no. So what I want to do next is I'm writing a proposal to run a bunch of zooms where we can actually capture the globular clusters, but at the moment we don't. I think because they hit the central galaxy when it's too gas rich, and you have a lot of a compression of the gas. I think that's a mechanism, a viable mechanism to create these globular clusters, but I need to run this into the check. 10 to the 20 megaparsec cube. So if observers, so the question is how rare are these galaxies? And my answer is if you look at massive galaxies with at least 10 to the 11 solar masses, a third of them should have a satellite with little dark matter. I'm not only looking at redshift here. So who knows what's going to happen in redshift. There could be other mechanisms of the redshift. And we have a oh, Jorge, like me. Mhm. Mhm. So the question is, in addition to these kinds of galaxies, you could also have tidal dwarfs. And the idea of tidal dwarfs, and you can correct me if I'm wrong, is usually when you have an interaction of two gas-rich galaxies, you have this tidal tail. Those tails can be the clumps in those tails can become their own galaxies and fly off, and they would be dark matter deficient and gas rich at birth. We don't. I checked entire simulation. We don't find any at this resolution. It doesn't mean that they don't exist. It's just that at the resolution which we don't find. I found a few clumps, but they have so few particles that I didn't trust them. I didn't include them in catalog. I'm going to wait until we finish running Firebox high resolution, and I expect to find some there. Okay. Mhm. Mhm. So what's the problem? Yes. Mhm. Oh, because of the gizmo is adapted. So yeah, and so basically we can achieve extremely high spatial resolution because it's an adaptive code. But what? Yeah, and I don't know the details of that. We need to ask for or Phil. Yeah. Yeah, the paper is on the archive. Maybe they give you some insight. Mhm. 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 Let me see if I can pull up. So, okay, so here I'm showing you on the y-axis, I'm showing you the fraction of dark matter retained from info to today. On the y-axis, I'm showing you the fraction of stellar mass retained. And you see that the dark matter between galaxies, they lose both, but they lose more dark matter than stellar. We check the power radius, and that's not a problem. Well, at least for Firebox, because that's not a problem. It might be a problem if we keep running the simulation at this resolution forward. But from the moment it becomes dark matter efficient until today, that's not a problem. Numerical distribution is not a problem. And you can see the supplementary materials in the paper. We talked more about that. And it seems like that's it. Yeah. Thank you for your generous attention.